Hi guys and girls, in this video I will tell you about quantum mechanics as a science. Quantum mechanics is a fundamental physics theory that expands, refines and combines the result of classical mechanics and classical electrodynamics in the description of microscopic objects. This theory is the basic for many areas of physics and chemistry and covers solid-state physics, quantum chemistry and particle physics. The term quantum from the Latin quantum how much is associated with discrete portions that the theory gives to contain physical quantities such as the energy of an electromagnetic wave. Quantum mechanics (QM), also known as quantum physics, quantum theory, wave mechanics, or matrix mechanics, encompasses quantum field theory and is a fundamental theory of physics that describes nature at the smallest scales of atoms and subatomic particles. Classical physics, which existed before the formulation of the theory of relativity and quantum mechanics, describes nature at the ordinary macroscopic level. Most theories of classical physics can be derived from quantum mechanics as an approximation that operates on a large macroscopic scale. Quantum mechanics differs from classical physics in that energy, momentum, and the other quantities of a related system are limited to discrete values. Mechanics is the science that describes the motion of bodies and the corresponding physical quantities such as energy or momentum. The development of classical mechanics has led to significant progress in understanding the world around us, but it has its limitations. Quantum mechanics gives more accurate and true results for many phenomena. This applies both to phenomena of microscopic scale. Here classical mechanics cannot even explain the existence of a stable atom, and to some macroscopic phenomena, such as superconductive superfluidity or radiation of an absolutely black body. For centuries, quantum mechanics and its predictions have never been challenged by experiment. Quantum mechanics explains at least three types of phenomena that classical mechanics and classical electrodynamics cannot describe. Quantization of some physics quantities, the existence of wave properties in particles and corpuscular properties in radiation, corpuscular wave dualism, existence of mixed quantum states. Physical foundation of quantum mechanics. The unquestionably principle states that there are fundamental obstacles to accurately measuring two or more parameters of a system with arbitrary error. In the example of a free particle, this means that it is fundamentally impossible to find such a waveform function that would be the eigenstate of both the momentum and the coordinates. It follows that the coordinate and momentum cannot be determined simultaneously with an arbitrary error. As the accuracy of coordinate measurement increases the maximum accuracy of pulse measurement decreases and vice versa. Those parameters for which such a statement is true are called canonically conjugate. Interaction with other theories. The fundamental principles of quantum mechanics are quite abstract. They claim that the state space of the system is Hilbert space and that the physical quantities correspond to the Hermitian operators operating in this space but do not specify what a Hilbert space is and what kind of operators. They must be selected appropriately to obtain a quantitative description of the quantum system. An important guideline here is the principle of conformity, which states that quantum mechanical effects case to be significant and the system acquires the features of the classical with increasing size. This big system limit is also called the classical limit or compliance limit. On the other hand, we can start by considering the classical model of the system and then try to understand which quantum model corresponds to the classical one, which is outside the correspondence limit. When quantum mechanics was first formulated, it was applied to models that corresponded to classical models of non-relativistic mechanics. For example, the Gauss model of a quantum harmonic oscillator uses an openly non-relativistic description of the kinetic energy of the oscillator as well as the corresponding quantum model. The first attempts to link quantum mechanics with special relativity led to the replacement of the Schrödinger equation with the Dirac equation. Those theories have been successful in explaining many experimental results, but have ignored facts such as relativistic or creation and the annihilation of elementary particles. Completely relativistic quantum theory requires the development of quantum field theory, which will apply the concept of quantization to their field rather than to a fixed list of particles. Completely relative quantum theory requires the development of quantum field theory, which will apply the concept of quantization to the field rather than to a fixed list of particles. The first completed quantum field theory, quantum electrodynamics, provides a full quantum description of the other processes of electromagnetic interaction. The completely apparatus of quantum field theory is often redundant to describe electromagnetic systems. A simpler approach taken from quantum mechanics suggests that charged particles be considered quantum mechanical objects in a classical electromagnetic field. For example, the elementary quantum model of a hydrogen atom describes the electromagnetic field of an atom using the classical Coulomb potential, E inversely proportional to distance. This pseudo-classical approach does not work if quantum fluctuations in the electromagnetic field, such as the emission of photons by charged particles, began to play a significant role. Quantum field theories for strong and weak nuclear interactions have also been developed. Quantum field theory for strong interactions is called quantum chromodynamics and describes the interaction of subnuclear particles, quarks and gluons. Weak nuclear and electromagnetic interactions have been combined in their quantum forms into one quantum field theory, which is called the theory of electroweak interactions. It is not yet possible to build a quantum model of gravity, the last of the fundamental forces. Pseudo-classical approximations work for and have even predicted some effects such as Hawking radiation, but the formulation of a complete theory of quantum gravity is complicated by the existing contradictions between the general theory of relativity, the most accurate theory of gravity known today, and some fundamental provisions of quantum theory. The interaction of those contradictions is an area of active scientific research, and theories such as string theory are possible candidates for the title of future theory of quantum gravity. Application of quantum mechanics. Quantum mechanics has been a great success in explaining many environment phenomena. The behavior of microscopic particles that form all forms a matter of electrons, photons, neutrons, etc. can often be satisfactorily explained only by the methods of quantum mechanics. Quantum mechanics is important in understanding how individual atoms combine with each other to form chemical elements and compounds. The application of quantum mechanics to chemical processes is known as quantum chemistry. Quantum mechanics can provide a qualitatively new understanding of the processes of formation of chemical compounds, showing which molecules are more energy efficient than others and to what extent. Most of the calculations made in computational chemistry are based on quantum mechanical principles. Modern technology has already reached the point where quantum effects are becoming important. Examples are lasers, transistors, electron microscopes, magnetic resonance imaging. The study of semiconductors led to the invention of diodes and transistors, which are indispensable in modern electronics. Researchers today are looking for reliable methods of direct manipulation of quantum states. Successful attempts have been made to establish the principles of quantum cryptography, which will guarantee the secure transmission of information. A more distant goal is to develop quantum computers that are expected to be able to implement certain algorithms with much greater efficiency than classical computers. Another topic of active research is quantum teleportation, which deals with technologies for transmitting quantum states over long distance. Philosophical aspect of quantum mechanics. From the beginning of the great creation of quantum mechanics, its conclusions, which contradicted the traditional notion of world order, resulted in an active philosophical discussion and the emergence of many interpretations Even fundamental principles such as those formulated by Max Born on probability amplitudes and probability distributions have been waiting for decades for acceptance by the scientific community. Another problem with quantum mechanics is that the nature of the object it is studying is unknown. The sense that the coordinates of an object or the spatial distribution of the probability of its presence can be determined only if it has certain properties, charge or, for example, and environmental conditions, the presence of electric potential. The Copenhagen interpretation, thanks primarily to Niels Bohr, is the basic interpretation of quantum mechanics from its inception to the present day. She argued that the probabilistic nature of quantum mechanical predictions could not be explained in terms of some other deterministic theories and imposed that limitations on our knowledge of the environment. Quantum mechanics therefore gives only probabilistic results that the very nature of the universe is probabilistic, although determined in a new quantum sense. Albert Einstein, himself one of the founders of quantum theory, was uncomfortable with the fact that in this theory there is a departure from classical determination in determining the values of physical quantities of objects. He believed that the existence theory was incomplete and there should be some additional theory. Therefore, he put forward a series of remarks on quantum theory, the most famous of which was the so-called APR paradox. John Bell has shown that this paradox can lead to measurable difference in quantum theory, but experiments have shown that quantum mechanics is correct. However, some inconsistencies in those experiments leave questions that have not yet been answered. Everett's interpretation of multiple worlds formulated in 1956 offers a model of the world in which all possibilities for the acceptance by physical quantities of certain values in quantum theory occur simultaneously. In fact, in a multiverse assembled from predominantly independent parallel universes. The multiverse is deterministic, but we get the probabilistic behavior of the universe only because we cannot observe all the universe at once. History. The foundation of quantum mechanics were laid in the first half of the 20th century by Max Planck, Albert Einstein, Werner Heisenberg, Erwin Schrödinger, Max Born, Paul Dirac, Richard Feynman, and others. Some fundamental aspects of the theory still need to be clarified. In 1900, Max Planck proposed the concept of energy quantization in order to obtain the correct formula for the energy of radiation of an absolutely black body. In 1905, Einstein explained the nature of the photoelectric field, postulating that the energy of light is absorbed not continuously but in portions, which he called quanta. In 1913, Niels Bohr Bohr explained the configuration of the spectral lines of the hydrogen atom, again by quantization. In 1924, Louis de Broglie proposed the hypothesis of corpuscular wave dualism. Those theories, although successful, have been too fragmentary and together form the so-called old quantum theory. Modern quantum mechanics was born in 1925 when Heisenberg developed matrix mechanics and Schrödinger proposed wave mechanics and his equation. Janus von Neumann later proved that both approaches were equivalent. The next step came when Heisenberg formulated the uncertainty principle in 1927, and it was around the time that a probabilistic interpretation began to take shape. In 1927, Paul Dirac combined quantum mechanics with special relativity. He was also the first to apply operator theory, including the populator bracket notation. In 1932, John von Neumann formulated the mathematical basis of quantum mechanics based on operator theory. The era of quantum chemistry was started by Walter Kater and Fritz London, who in 1927 published a theory of the formation of covalent bonds in a hydrogen molecule. Later, quantum chemistry was developed by a large community of scientists around the world. In 1927, Key division and L. Gemmer demonstrated the diffraction of slow electrons on nickel crystals at the Bell Labs Research Center. When estimating the angular dependence of the intensity of the reflected electron beam, its compliance with the one predicted on the basis of the Wolf-Bragg condition for the de Broglie length waves was shown. Prior to the adoption of the Broglie's hypothesis, diffraction was regarded as an exclusively wave phenomenon. When the de Broglie wavelength was compared with the Wolf-Bragg condition, it was possible to observe a similar diffraction pattern for particles. Thus, de Broglie's hypothesis for the election was experimentally confirmed. Confirmation of the Broglie's hypothesis was a turning point in the development of quantum mechanics. Just as the Compton effect shows the corpuscular nature of light, the division-Gemmer experiment confirmed the inseparable coexistence of a particle and its wave. In other words, the inherent nature of corpuscular matter as well as wave nature. This served to formalize the ideas of corpuscular wave dualism. Confirmation of this idea for physics was an important step because it allowed not only to characterize any particle attribution to it a certain individual wavelength, but also in description phenomena to use it in the form of a certain value in wave equations. That is all. Thank you for watching. Goodbye.